let me hand it over to our next panel, moderated by Tom Kingsley, MD, PhD from Mayo Clinic, and he'll be speaking to Balaji Krishnamurthy, PhD from Adobe, and Ayush Chopra, who's a scientist at MIT. Handing over to Tom.
All right, thank you very much. I think Dr. Kanasti and Ayush are going to present first, and then I think we moderate. Would you guys want to start off with your presentation? We're really looking forward to hearing.
Sure. I'll start sharing the screen then.
All right. Okay. All right. Thank you. Yeah. Thank you, everyone, for joining our session. I'm very excited to present Deep-ABM, which is our tool for simulation to support the scenarios that will lead to our COVID-19 recovery. And this is a joint effort from a bunch of people from Adobe and MIT. And again, I'm pretty excited to talk about it. So let's get right down to it. Can we go to the next slide, please? So over the last 1 year, as we have been passing through the pandemic, we've been assailed by a series of what-if questions, both from an individual level as well as from a policy level. For example, there are many questions that still remain, right? What if we were to reopen the schools in the next 100 days or the near future? We have a 2-dose vaccine. So what if we delay the second dose in favor of vaccinating a larger number of population with a single dose? What if people, after getting cooped up inside for so long, after getting their initial dose of vaccination, start interacting a lot more and going out? What kind of effects it would have on the COVID-19 spread, right? So these are all questions that we need to answer. And before vaccines, we had this question about whether we should prioritize a faster but less specific test in favor of a test that has a higher turnaround time, but is much more specific. So the key challenge in estimating all of these is that the phenomenon that we are trying to model is very complex, and we really need very good tools to make very fast and better informed decisions, right? That's the need of the hour. Maybe we can go to the next slide. So to drill down deeper, let's just take one question, which is the case of whether we should go for policy-wise, we should prioritize a faster test versus for a more accurate test. So the intuitive answer could be that we should go for a more accurate test. But if we actually do a modeling under the assumption that we are looking at a population of individuals who have various behaviors and who are kind of heterogeneous in their behavior, and you take into account the fact that there is a time lag between the time the test is administered and the test results come out, and there is a lot of interaction between them, and you put all of those things in and you model it, then you come up with the kind of results that we have shown here, where administering tests that are having a much faster turnaround will have better outcomes for the whole population. So the answers to these questions are kind of non-intuitive, and it requires us to use modeling frameworks that are able to take individual people as agents and model all the effects that are going around them, and also take into account the various interactions they could have. So such models, such family of models are called agent-based models. And those models essentially enable us to simulate the action and interaction of multiple agents, and also be able to predict the population level effects. Can we go to the next slide? Right. So agent-based models are a really cool thing. And the graphic here is something that from an article on Wall Street Journal about agent-based models and their good properties. So you take each individual in the population as an agent who has a certain amount of connections, and then you can model the effects of how the information, or in this case, virus, transmits among the population. Right? So it is capable of representing interactions in heterogeneous population. It can support time varying actions, and pretty complex phenomena can be modeled here. All good, but traditionally ABMs are a very computationally expensive to run, and they're also very hard to implement and maintain because it's kind of difficult to do it in a normal standard way. And there is a lot of parameters and configurations that one needs to take care of, and traditional ABMs are really hard to configure and parameterize. However, if you really want these tools to work, then we need to make them make ABM scalable, efficient, and high performant. Right. Next slide, please. And this is exactly what the MIT Adobe team has done. Right? So what we have done is that we took ABMs and reimagined them in modern machine learning frameworks. So what we have by doing this, what we have done is that we take the local interactions of agents in an ABM and modeled it through what are called graph convolutions and implemented them on using tensor calculus. So once we are able to do this, we are able to achieve a large scale. We can support large agent populations, which are larger than 100,000 agents. We can utilize GPUs or graphics processing units, which are very efficient computational units, and be able to get you results in a very near real-time fashion. And we are able to also integrate diverse data sources, which are necessary to model such complex phenomena and give you very highly performant models. So by using this ABM tool, we are able to quickly evaluate a large number of diverse scenarios and be able to come up with good decisions. Next slide, please. Right. And in particular, for the COVID-19, what we have done is we took our ABM framework and we have added a whole bunch of configurable features to specifically support COVID-19 simulations. So the variables fall in COVID-19 simulations fall under three broad buckets. One is about how the agents or the population is interacting among themselves, and which we model it as interaction networks. The disease dynamics, about how the disease progresses. And the third one would be all the interventions that we could possibly have. Right? In terms of interaction, we model the interaction between people in three layers. One is that people interact among their households, and there is interaction with the people in the places of work, which is the occupation. And finally, there is a bunch of random interactions that happen as people go through their day. Right? And for disease dynamics, we have ability to do a very granular stages of infection. We know that the dynamics of the disease is stratified by age, and we have taken care of all of that, taken account of that in the model. And we also have support for modeling diverse strains. Like we now have a new strain that is coming in, especially in Europe and other areas. We could model all of that. And in terms of interventions, we have all of the current things that we have, which is quarantine, notification of exposure, various forms of testing, vaccination, and so on. So these are all, so we have a very configurable tool, which is, which you can use it at a programmatic level, as well as a modular and an intuitive UI with which we can experiment with it, right? And next slide. Yeah, so I think I'm going to hand it over to Ayush, who can walk you through a demo of what our tool does, specifically for COVID-19, and then I can come back and wrap it. Ayush, you can start.
Thank you, Balaji. Hi. So to make it easier for the real experts to iterate, make quick decisions, we augment Deep-ABM with a simple and intuitive interface that can help seamless experimentation. Basically, our goal is fourfold. We wanted to add modularity to the system, so through a plug and play interface, so that you can customize experiments for the different kinds of networks, disease dynamics, and the kinds of interventions you would want to try out. We wanted to bring in granularity so that experts can have fine-grained control over various social, behavioral, and clinical assumptions that parameterize the agent-based model and our interactions in society. And we wanted to do this with a lot of flexibility so that we can have fast experimentation, iteration, and hypothesis testing, as well as sensitivity analysis. And our tool, the efficiency of our tool makes it possible since we can run results in real time on large agent population. So I'll now walk us through a real interactive demo of how the tool works. So this is the tool dashboard. So the Deep-ABM window consists of a setup on the left and an option to then run experiments. So have a very modular experience. We allow experimenters to specify the dynamics for the specific kind of agent population they want to work with. So first we import the population dynamics, which can be a simple CSV, which specifies what two agents look like and how they interact with each other. We can then specify the specific properties of the infection that we are modeling. These are usually clinical parameters, which an expert may want to change based on the specific kind of experiments. Next, we can select one or many different interventions and have granular control for each of them. In particular, we support 4 interventions. You can do exposure notification, where you can specify what would be an assumed adoption and compliance rate to model social behavior. We can specify symptomatic testing, which may involve using RT-PCR or antigen tests. We can specify parameters for vaccination, as well as for different kinds of rapid point of care testing. For vaccination, we may want to simulate what happens if we do double doses on schedule, or if there is a delay in second dose. Let's choose a scheduled double dose for the moment. We can also choose and experiment with what if the efficacy of the single dose vaccine is different. So we know that the efficacy of the 2-dose vaccine is 95%, but what if the efficacy of a single dose is 90%? And then we can also tweak and study the effect of changes in daily administration rates of vaccines. So let's run a simple experiment. So the Deep-ABM tool runs this experiment in real time and helps us visualize the cumulative infection, mortality, and hospitalizations over a period of 6 months through the simulation. Now, we may want to tweak and study the effect of granular changes in parameters. For instance, what if we increase the daily administration rate to 100%, to 1% of the population per day? And we also have this option to do persistent comparison so that each additional experiment can be compared with all previous experiments we've run. So when we rerun this experiment, we see that, as expected, there is significant decrease in mortality, hospitalization, and cumulative infections on increasing the daily vaccination rate. While this is very useful, we realize that in ramping up vaccination rates can take time, and there is a short ramp up time. So in the meanwhile, we want to ask this question: what if we use additional intervention strategies to maximize the effect of our current vaccination load? So in this rate, there has been a lot of discussion around using random point of care tests to identify pre-symptomatic agents and quarantine them beforehand so that there is decrease in viral spread. So we simulate the study at our current experimental rates, at our current vaccine efficacy rate, and we can run a new experiment just by changing a single parameter. And the purple line represents the setup where we augment the daily vaccination rate in our current setup and augment this with random point of care tests. And we realize that there is a significant decrease in mortality, deaths, and hospitalizations. So we can use the Deep-ABM can help us consider that using random point of care testing can be a good alternative to augment our current vaccination strategies while we ramp up daily vaccination rates. So we've used this tool to study a lot more other parameters as well. So for instance, the scientists and clinicians and health experts at Mayo Clinic, Arizona, and Harvard University, we collaborated with them to study what if we delay the second vaccination dose. And we realized that under the current parameter configurations, delaying second dose in favor of the first dose can lead to a nearly 20% reduction in deaths. Apart from clinical considerations, Deep-ABM can also be extremely valuable for social messaging. For instance, the last year has been hard on everybody, and we're eagerly waiting for vaccination so that we can go back to our daily lives. So we wanted to study what if people increase interactions immediately after taking the first dose. To analyze this, we studied the effect of 2x, 4x, and 8x increase in random interactions after the first dose is administered. And we realized that there is a chance of significant increase in deaths, nearly 2x, even with continued vaccination. So vaccination parties will have to wait. So these are important messages which government and policy making decisions departments might need to consider so as to ensure safe recovery from the COVID vaccine, from COVID. Back to you, Balaji.
Thank you, Ayush. So this tool, the Deep-ABM tool, has a lot of potential, not beyond COVID, also in multiple areas. For example, in public health, you can use the Deep-ABM to find out the effect of personalized notifications, what's the effect of knowledge dissemination, and so on. And certainly will be useful in other epidemics that will follow. In terms of economics, you can look at Deep-ABMs for modeling how the economy will recover from a shock like the current one. You can also look at ABMs for fiscal policy, monetary policy, and other such economic questions. In terms of business, you can look at, you can use the Deep-ABMs to ABM to look at the effect of social interactions, to measure what would happen with personalized offers, and how to conduct more effective brand messaging campaigns. And one more good thing about the Deep-ABM work that we've done is that since we have fused a machine learning framework along with ABMs, it allows us to do learning on top of ABMs and be able to adapt behavior from one agent community into another. So plenty of opportunities are available. And I'm really hoping that we can collaborate with all of you to take this tool and put it to good use so that we can get back quickly to our lives and take the key policy decisions based upon proper simulation and considering all factors, right? So, so next slide, please. So again, an invitation to reach out to us and collaborate with us. You can use a QR code over there, or if you prefer a human readable thing, then we have our contact details right here. Thanks a lot. And over back to you.
Yeah, I want to thank you, Balaji and Ayush. This is absolutely brilliant work. Couple questions for you guys. So when you were approaching this, you know, one of the things with ABM models is that they're typically slow to build. Looks like what you guys have done would allow for kind of fast iterations and answering questions quickly, which we've realized from a healthcare perspective, public health perspective is so important. You know, one of the things that you said that this model allows is modularity. How do you anticipate some of the questions, the policy questions, or the experiments that are going to be needed, and how quickly can you change these experiments using this technique that you guys have described?
Right. So the key set of things, as I pointed out, where there is the interaction networks is one of the things that would change if you get better data or newer data on how people would interact. That would change, and disease dynamics would be the other one, which is always changing as you get more and more data. So these are files that you can configure and then run the setup. It would be as simple as changing some parameters over there and running it. Wouldn't cost too much of tweaking about the model itself.
Yeah.
So we could essentially also, we could even come to a point where we can change the network over time, and it need not be a fixed network. It's not as if there's a fixed network that is that's being modeled throughout. So even that flexibility is there. So.
Right. And how do you guys see this being used in the future? I mean, I see a lot of potential in this tool. Obviously, right now for COVID, this could be incredibly valuable for some of the things that you guys are both mentioning, Ayush was talking about, delaying a second dose, people's behavior based on their understanding of, their immunity status. How do we use this tool though? How do you imagine this tool being used in the future, maybe even outside of COVID? Because it seems like there's a lot of potential here for a lot of different applications.
Right. So I touched upon a few of the possible applications. So the first thing would be how does as the economy opens up, we could answer questions specifically about whether what would be the effect of travel, right? So how if as people start traveling, what kind of effects that would you see, and how quickly you need to vaccinate so that the businesses can get back, so that they can get back, and the economy can get back get back on track. So these are business level questions that you can answer. You can also answer questions in the economics domain, really about, because ultimately this is about agents who are acting in aggregate fashion, and that's the net effect of economy. So you can use it to model economics. So these are some of those questions that we think can benefit from doing this tool. Yeah, using this tool. Yeah,
that's great. I see that a lot of potential in especially in the healthcare space. I'm curious, some of the things like having, vaccine, or having, some of the testing. What if we wanted to look at a new element of, COVID? Let's say maybe it was some new aspect, a new test that had been passed by the FDA. How quickly can we update this current model if a new test was to be passed, and do an experimentation? Maybe I'll ask Ayush to.
so you want to take that, Ayush?
Sure, I'll do that. Yeah. So basically, we support all of these configurations off the shelf. So to add any of these, for example, to add a new test, you just need to basically input a new configuration file, the way we uploaded the CSV for the disease dynamics. So a test can be a part of that same configuration. You may also use it as part of your population dynamics, and it's just as simple as uploading a file for you. We support the basic infrastructure for doing these interventions. Different instances of or different copies of these interventions may change. For example, we see the granular control for vaccination. It's very straightforward to add that same control for random point of care testing as well. And once we do that, you can try out as many tests as you would like.
So really, you just need the configuration file. You can, the way that you've had it designed, you can upload that configuration file, and the model will adapt to that those new parameters.
Yes.
Yes.
Oh, it's very impressive. Well, thank you both. This is brilliant work. I think we are out of time, at least what I was told. So was our kind of finishing timeline here. Any last thoughts about what you're going to do with this model in the near term, in terms of maybe updates or modifications?
I think so. We've already been working on building support for multiple viral variants, which may spread in the society at the same time. And we want to generally also focus on building support that can extend for that can move towards the post facto effects of vaccine distribution. For example, what if the vaccine does not last? What if the vaccine only lasts for 12 months? Or what if it decays in a particular fashion?
Right.
What if people do not come back for a second dose? Like, there'll be a lot of important questions that we need to consider. And those are questions we are ready to support. And we would love for expert clinicians like you to point us to the right questions and use the tool and make it.
Those are critical. Yeah, those are critical questions. And,
Right.
this allows us to, having a tool like this allowing us to answer these questions is, can't tell you how important that is. I mean, really, to do empiric research just takes too long in these kind of pressure cooker situations that we're in, like right now with COVID. And so having a tool like this really gives us some information that otherwise we wouldn't be able to have. And I just want to thank you both. I mean, this really could impact lives and allow us to make better policy decisions and healthcare decisions. So just want to thank you for your work on this.
Thanks a lot. It was it was a very exciting time, and we really look forward to collaborating with experts in framing the questions, and we'll be happy to provide the support. Thank you.